Not sure how I'm coming through. It looked like there was a little bit of a glitch, so I'm going to give it a couple seconds. You'll see that the first two that I'm looking at right now are review from Monday. I am not going to do the Pythagorean theorem. What I am going to do is strictly use our formulas that we talked about on Monday. Hey, Reagan. So again, I'm not going to use the Pythagorean theorem. That is a strategy. That is something that you absolutely can do. Hi, Natalie. What I am going to do, though, is just use our formulas. So the first thing I recognize is that this is a 45, 45, 90. Hi, Irene. Hi, McKenna. And I'm going to place opposite the congruent sides our formula A, and then opposite our 90-degree angle is our A radical 2. Hi, Sarah. So again, not doing the Pythagorean theorem today, just using our formulas. And we're supposed to remember that the side that has the length and the formula, we're going to set equal to each other. Hi, Landon. So we're going to set these two equal to each other. And we're going to solve. So again, just make sure we divide by that radical. And when we divide by the radical, we end up with an inappropriate answer. It will not be allowed. So we end up with A equals 64 over radical 2, which means we have to rationalize. So again, this is something that we talked about at the beginning of the year, and I know I'm annoyingly saying that, but we have to rationalize that, which means make the denominator a perfect square. Now, the nice part about our special rights is that the number that's going to make it a perfect square is going to actually be the number you're looking at. Algebraically, there are shortcuts to this later that make it go a little faster, but what's really nice about special rights is this is a prime number, so the only thing that's going to work is multiplying top and bottom by itself. So that's the rationalizing part, getting that out of the denominator. And we are going to multiply straight across, which is the original denominator. We now find that the radical 2 has shown up on the top, and on the bottom, we end up multiplying those together and we get radical 4. So what ends up happening is we have our original numerator, the radical 2 that showed up on the top, and now just 2 on the bottom. That pattern holds every time. So again, if you're looking to cut back on the amount of time you're spending, just remember, yank the radical to the top, just the number, the radicand, that number inside, on the bottom. It happens every time, no matter what that numerator is. It would be numerator, the original denominator, over just what's inside. So the last thing that you have to do, though, is make sure you do simplify, and 64 divided by 2 is going to be 32. So we end up with 32 radical 2. Now, if you are also recognizing a pattern, notice how 32 is half of 64. It will be that every time. So our x and our y in our final answer, because it is isosceles, we would write x equals 32 radical 2, y equals 32 radical 2. And don't talk about me, I just realized I wrote my 2's in both situations differently. Yep. So the biggest thing here isn't so much the formula, it's making sure that we remember how to rationalize so that we have our appropriate answer. So just one more to look at. Same idea, we recognize that it is in fact isosceles. And I have an A in this problem, so I'm not going to use A for my formula. Again, it really doesn't matter what the variable is as long as it's a 1-to-1 to radical 2 ratio. I'm going to use, let's use X. So X, X, and X radical 2. Now again, what we're supposed to do is look to see which side has the formula and which side has the number. So that does. So what we know is if we set them equal to each other, we already have figured out what X is. So make sure here for A, you already know the answer. It's 2 radical 7. But for X radical 2, we need to make sure that we plug in the appropriate X value. So that means X, which is 2 radical 7, will multiply by that radical 2. And the radicals will go together. We're going to multiply those together. You end up with 2 radical 14 for the hypotenuse. So again, when we write our answer, A is 2 radical 7, and B is 2 radical 14. And we're done. Now, most of these questions, though, are supposed to be pretty quick, and that's why we have these new formulas, these patterns, if you will. And it's, again, so that we don't have to rely on our Pythagorean theorem to bail us out. So last, let's just look at one last example for our 45, 45, 90. $57 millimeters. Now I do like some of the questions. I will say, come up, find all the measures. Well, when it does say find all the measures, it not only means X and Y, but it also means whatever value hasn't been labeled. So for instance, if this had ABC around the triangle, you'd have to label that as also 45 degrees. So just keep that in mind that sometimes those questions do pop up. Should not be anything we aren't capable of doing now at this point. So knowing that these formulas, these special rights are supposed to make things easier on us, A radical 2. I already see that this guy is 57. I know for a fact that because the sides, that this is isosceles, right away I know this guy's going to have to be 57. And if A is 57, I can plug that in, and I already know that that's 57 radical 2. My work is finished. I don't have to do any extra work here because the pattern is what it's supposed to be. And I can simply write X is 57, Y is 57 radical 2. And we're done. So that's kind of the purpose of this, is so that you can see that it can be much faster than the Pythagorean theorem. And in most cases, that's what we're looking to do in a lot of our beginning, is explain why it happens and then show you that there are many ways to make these go by faster. So with that, are there any questions that I can answer before we move on to the next special right triangle? Okay. We then are going to tackle 30, 60, 90. And for all of you that did look at your formula sheet on Monday, you already noticed that this was on your formula sheet. Now, because you saw that this ideally all kind of comes from a pattern, at least you saw with it being referred to as a special right with our isosceles triangle, you kind of saw that with our Pythagorean theorem, the pattern held every time. So similarly with our 30, 60, 90, there is that pattern that gets held to every time. Now, I'm not going to go through the Pythagorean theorem simply because it's fairly extensive, includes quadratics, and at this point, I think just the idea that you know that it came from somewhere, that someone just didn't make it up and go, ooh, it worked. We're going to look at a right triangle. Notice this time it is scalene. One angle is clearly smaller than the other. And we are going to label these, and it is very, very important that you know which one is the 30 and which one is the 60. If you just put your formula around this triangle any which way, it does not work. So it is very important to know where each of these angles are located. So with 30, 60, 90, there is a special formula that we're going to use, and opposite our 30-degree angle is going to be A. Just like in our isosceles, we have to start somewhere. So opposite our 30, so in this direction, opposite our 30-degree angle is A. Opposite our 60-degree angle, so the longer side, keep that in mind that we're still using this triangle inequality stuff. Opposite the 60-degree angle is our longer leg, that is A radical 3. Our longest side, which is the hypotenuse, opposite that 90-degree angle is going to be 2A. So our formula this time is different. We have a different radical that comes into play. And now we have 1A, radical 3A, 2A. It's scalene, so all three sides should be different because all three angles are different. And we talk about the ratio of our sides, just like we did with our isosceles. It is in a 1 to radical 3 to 2 ratio. Again, the letter A for the variable means nothing. It could have been G radical 3, G, and 2G. Could have been M radical 3, 2M. It doesn't matter. What matters is that the ratio of the sides, we have our shortest side, our middle length, and our longest side. That's what matters. Now, what you saw us do with our 45, 45, 90, we're going to do with our 30, 60, 90. Same setup. We're going to identify our sides. We're going to label them with our formula, and we're going to solve the same way. So let's start off with our pretty much our same picture. Okay, here's a situation where we're going to solve for the whole right triangle, meaning we're going to find every measure. Well, we already have 90. We already have 30, which means we only need 30's complement. We then have to find x and y, and here again, the Pythagorean theorem is not going to even remotely be the easiest way. It would be the most time-consuming way. So that's why I'm not even going to introduce it as an option. What we are going to do is we're going to put our formula around it. So I am going to identify what angle C is, the complement, that's 60, which does mean I can already fill that answer in. Now that I know where my angles are, 30, 60, 90, opposite the 30, I'm going to put my formula A. Opposite the 60 is A radical 3. Opposite the 90 is 2A. Notice I keep saying opposite the angle, and that's because it's the most important concept. I'm not just putting A down here because it's at the bottom. I'm not putting the A radical 3 over here because it's at the left. It's because it's opposite the angles, and we've done a lot with that. At this point, every step is the same as what we just got done doing. We find the side that has the value and the formula. We set them equal to each other, and we use the value for A to plug in each of these situations. So now that I know A is 12, I know that this side has to be 12 radical 3. Because I know A is 12 and I plug 12 in here, so 2 times 12, I now know this side is 24. Again, the purpose of this is to save a considerable amount of time. So I come back up here, 12 radical 3, 24, and I'm done. So let's look at another side as our given length. My dog sounds like a motor in the other room. I'm not sure what he's upset about. But he doesn't even sound like he's got enough energy to get off the couch to figure it out. All right. So we are going to label that guy as 32. I'm going to give you that one is 60. And the directions would be find the measure of angle X, Y, Z, and X. Oops, X, Y. So, first step, fill in the missing piece, which is the 30. Second step, write your formula all the way around. Now I moved things so that you can see that it's important for us to know where the 30-degree angle is, and we go opposite that 30-degree angle to start our 1 of something. So let's go with M, 1M. Opposite our 60 would be M radical 3. And opposite our 90 is 2M. Notice how I'm still using different colors so you can see your formula apart from all the other work that you're doing. Notice I also didn't use a radical 3, and 2a. Doesn't matter. It's a 1 to radical 3 to 2 relationship. So right away we knew that that other angle had to be 30 degrees. And I do what I did before. Find the side with the value and the formula and set them equal to each other. 2m equals 32. And we find out m is 16. So that means this side is just 16, and this side is 16 radical 3. Done. There he goes. He warmed up. For the record, there is not a soul outside. All right. Every example is going to have the same steps. Find your angles, label your formula, solve for m. So the only thing that I'm going to add now are 2 more examples that involve our radicals, and we're done for the day. Because truly what happens is when we deal with the rationalizing, that's when things get a little hairy. So let's bring radicals into a few of our examples. And I lied. It's going to be 3 examples just to prove a point. All right, so we want to find the measure of angle P, X, and Y. Again, just to stress that we need to know what our angles are. It's very important to know where they're at. So the measure of angle P is going to be 60 degrees. Second step, same every time. Label your sides according to the formula. So opposite the 30 is A. Opposite the 60 is A radical 3. Opposite the 90 is 2A. The side that has the value and the formula, set them equal to each other. So A radical 3 equals 7 radical 3. You can hear what A is even as you say it. But if you need to see it again mathematically, just like you saw with our 45, 45, 90, you can divide away that radical 3 and it cancels on both sides. So it's not just that we guessed A was 7, it mathematically proves by division that it is 7, which means this side is 7, and this side is 2 times 7, or 14. So what's X? 7. What's Y? 14. So again, the reason why these formulas, I know I'm annoyingly saying it over and over and over again, but I do want you to realize there is a purpose for why we introduce it, and it is to cut back tremendously. Think about those of you who know what the Pythagorean triples are. You cut out so much work just by knowing what 3, 4, 5 or 5, 12, 13. So that does help. So let's throw a radical in a different way. Yeah, we'll go with this number first. All right, so we want to find x and y. And I don't really care now about the other measure, but you still should label it just to keep yourself straight. And then label your formula. Opposite the 30 is a. Opposite the 60 is a radical 3. Opposite the 90 is 2a. Again, opposite the angle is how I know where to put the formula. Opposite the angle, opposite the angle. And once I have my formula, the side that has the value and the formula, I set equal to each other. So a radical 3 is going to be equal to 15. To get a by itself, we're not going to change math. Math stays the same. We're going to divide by that radical 3. And what happens is, let's change him for this. And we're going to end up canceling over here, but we end up with a equals 15 over the square root of 3. And we can't have that. We have to rationalize. Again, the nice part about our special rights is the numbers that show up in the denominator, they're prime numbers. So there is no what works best. The only thing that's going to be best is by multiplying by itself. So when we rationalize, we now have 3 times 3 would give us that perfect square in the denominator. But look again at our pattern. The original numerator and that radical are now in our numerator. And we end up with 15 radical 3 over 3. So in the 45, 45, 90, where that radical 2 showed up, it's the same thing that's happening here, but because this uses radical 3, it's the original numerator with our denominator, just the radicand. So 15 radical 3 over 3. Only thing you have to do is make sure you reduce. Since 15 can be reduced by 3, this ends up simplifying to 5 radical 3. So all this work is to say that A is 5 radical 3, which means I now know this side is 5 radical 3. And I know this side is 2 times 5 radical 3, or 10 radical 3. So when we write our final answer, x is 5 radical 3 and y is 10 radical 3. Now, in my experience as a 21-year teaching veteran, please, before you write your final answer in anything, whether it's in a no reassignment, whether it's a written assignment, whether it's a standardized test that you'll eventually take, because you're going to see these come up again in Algebra 2, in pre-calc, in calculus. They're parts of problems now. They're not just the problem. Pay attention to what you've labeled. I've had on a number of times people tell me that this side over here, because they're not paying attention, is 10 radical 3. This side is 5 radical 3. That makes no sense. This side is clearly shorter than this side, so the numbers should work. So proofread as you're going. All right, so last example, and then we will leave Friday up to what you may or may not need. So let's do this. Because we know not everything is going to work out real nice and neat. Purposely putting that prime number there. And again, we're going to find x and y. No tricks. We are still going to put our formulas around this. So opposite our 60 is A. Oh, did you hear what I said? Excuse me. Opposite our 30. Opposite our 30 is A. Opposite our 60 is A radical 3. Opposite our 90 is 2A. Somebody turned him on. Brady! Opposite our 30 is A. Opposite our 60 is A radical 3. Opposite our 90 is 2A. So again, we're working with opposite our angles. And the side that has the value and the formula we set equal to each other. So A radical 3 equals 17. We divide away our radical 3 to get A by itself. And we end up being left with this value that as a final answer is inappropriate as a final answer. So we have to rationalize, which means make the denominator a perfect square. So to do that, 3 times 3 will give us the perfect square 9. And what we do to the bottom, we have to do to the top, so that again, we're multiplying by a number 1. That's what this really reduces to, is 1. And 1 times anything is itself. So it's just going to look different. It's not going to have a different value. And that pattern shows up. The numerator, the radical, and just the radicand on the bottom. So the minute I see 17 over radical 3, some of us may be able to already jump to 17 radical 3 over 3 because we recognize that pattern. There is no way to simplify. So we've already seen in other problems that you may have to, especially, and that's honestly, as much as you guys hate it, the one thing that I see really, really valuable with the no reassignments is that it makes us very conscientious to do answers like this, because these are the math answers as we go further and further in math that are going to show up. Not the nice whole numbers like 10 or 15. It's this stuff that shows up when we're really working. So if we now know that A is 17 radical 3 over 3, I know that's what this side is. 17 radical 3 over 3. And over here, I know I'm going to have 2 times 17 radical 3 over 3. Well, the 2 and the 3 aren't going to cancel, so I'm just going to multiply, and we find out this side is 34 radical 3 over 3. And maybe you don't like doing your work around the triangle like I am. You can then line it up real nice and neat. The easiest for me, though, is you will, if you have written work, write it out separately so there's no guesswork. And box it in. Brady! So, that is the last example. You will check Google Classroom. I know right now I already gave you the isosceles right triangle work to do. I'm going to give you just some practice problems to look at. Those won't be required. It's probably going to be either a worksheet that I had stored from days past, or just like a study guide where you'll already see the answers. So kind of look for that right now. I'm going to take a look at what we've already assigned in No-Re. I don't want to overwhelm you with required assignments, but you will see required assignments on both our 45-45-90 and our 30-60-90 very soon. So, well, hello. Now he's come to visit. If you have any questions, email me. Check Google Classroom for your updates so that you know what we will be doing. And I hope to talk to you soon. Please do something fun today. Move around. Don't just sit and do work and stare at a TV or a screen of some kind. But get up and move around and do something. Email me if you have any questions, and I truly hope to talk to you guys soon. Have a great day, and thank you. You loudmouth. A big boy.